Okay, so how is everyone today? Good? All right. So last time, what were we talking about? We talked about Fibonacci. That's what we were talking about the last time. And let's see, today's the 20th? That means that we're right at the equinox, right? Either today or tomorrow is going to be the equinox. What does that mean? Yeah, fall begins. Yeah, I guess. But it's the day on which the number of seconds of daylight of sunshine is the same as the number of seconds is nighttime. So we're about at 12 and 12 right now, and we're going to continue our descent until the fall, until the solstice, the day with the fewest seconds. Good. Fine. So we were talking about Fibonacci. And in particular, we did the slow way. I hope you remember that I evaluated Fibonacci of 7 sort of in this really tedious way at the beginning of the semester. That was awful. And last lecture we figured out how to write a function that evaluates the Fibonacci sequence sort of in the way that a human usually does it, by remembering 2 and calculating the next one, and then forgetting 1 and then calculating the next pair, next pair, next pair, next pair. So we did that, and in addition to that, we also introduced the concept of a matrix and a vector, just very lightly. And it turns out that to calculate the 100th Fibonacci number, you can take that matrix that we were talking about and multiply that matrix by itself 100 times. So if we name that matrix, I think we named it H. I don't know, doesn't matter. Big H. You could make 100 copies of Big H and then multiply them all together. 100 matrix multiplications. But the claim that we were making last time is that so if you wanted to find the 100th Fibonacci number, on the one hand you could do it the human way and take basically 100 steps to say, like, I know the first pair and I can find the next pair and the next pair and the next pair and the next pair, and just sort of march down the line one at a time with 100 steps. But the claim is that with that matrix idea, in fact, we can do it in far less than 100 steps. And it's not entirely clear. From last time, it's not entirely clear how we're going to do that. Okay, so that's one of the things we're going to do today. Another thing that we're going to do today, well, I'll show you. So here's that same mult in our function that we've looked at so many times. Its signature is, it's naturals cross reals. To reals. And its purpose is to define what it means to multiply a natural and a real. Of course, you already knew how to do that. Like if I asked you to just perform a multiplication. But here we're assuming that all we know how to do is add. So mult in R of n and x, its definition is, well, we've got 2 clauses. So when we're at the least natural, we're asking about n multiplied by x. So in particular, that would be 0 multiplied by x. So the answer is 0. And then otherwise, the answer is going to be x plus mult in R n minus 1 x. And this is just encoding the thing that you already know. If I was asking you to calculate 5x, well, That's x plus 4x's. That's what that's saying. Now, if we wanted to evaluate this, I'm going to evaluate something by hand. So, for example, I'll evaluate this. If I want to do mult in R with 4 and 10, say, then we're asking about what's 4 multiplied by 10. Now, of course, we know that's 40. Okay, but I want to show you the way a machine evaluates this, essentially. So, because the first argument is 4, that means that we'll use the second clause, because we're only going to use the first clause, the clause that exits, when this argument finally reaches 0. So it'll be 10 plus mult in R of 3 and 10. Okay, so then now, from a machine's point of view, it ignores this 10 and this plus because it knows what that means. So it has to move on to consider, what about this part? So conceptually what happens is the machine makes a new place to work, and you can kind of think of that like a pair of parentheses. And what it's going to do is it's going to replace whatever that is with its definition. So here it gets another 10, and mult in R of 2 and 10, like that. And from a human point of view, you would sort of probably naturally just not write those parentheses, and you might write 10 plus 10, but you might even just write 20, if this were a human doing this. But that's not how the machine does it. And it continues with this behavior. It says, 10 plus, and then it sees, oh, you're asking me to do that, so I'm going to make a new place where I could work, and then, okay, that's going to end up being 10 plus mult in R of 1 and 10, like that. So close, 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 close. And then doing that, okay, well, this will be 10 plus 10 plus 10 plus 10 plus mult in R, 0 and 10, and then close, close, close. And then finally, 10 plus 10 plus 10 plus 10 plus 0, close, close, close. Okay, now, addition is associative, which means that more or less we can just delete all those parentheses. So is that in fact 40? It is. But this is how the machine understands your instructions. It's doing something that's roughly very equivalent to this. It's keeping all those parentheses until the very end, and then it's like unwinding itself. It drops these parentheses and then says 10 plus 0, I can do that, and then drops the parentheses around that, 10 plus 10, okay. Drops those parentheses, 10 plus 20, okay. Drops those parentheses, 10 plus whatever, I forgot what I was saying, but that's how it does it. So this is a lot of bookkeeping. Bookkeeping is a funny word because it has 2 O's and then 2 K's and then 2 E's. It's kind of funny. I don't know of any other words exactly like that, where they have a pair and a pair and a pair. So notice that concerning this evaluation, numbering these clauses the way we usually do, from here to here we used clause 2, clause 2, clause 2, clause 2, and then finally clause 1. So the way it works is that whatever this n is, that's how many times you're going to evaluate clause 2, and then you're always going to have one more to exit clause 1. So if this was 110, so if we wanted to multiply 110, we would evaluate clause 2 100 times and then clause 1 once. So effectively, we're saying that to multiply by 100 requires 101 steps. But you know, we'd like to be able to do it a lot faster than that. Okay, so there's two problems. We want to do less bookkeeping. Okay, so that we don't have all this parentheses blow up. And also, we'd like to use far fewer steps. So this is what we want. It's like our wish list. Okay. So, meaning to say that, you know, according to this definition, to multiply by 100, it requires 101 steps. To multiply by 1,000,000 requires 1,000,001 steps. So what I'm telling you is that by the end of the day, to multiply by 1,000,000, it's only going to take about 20 steps. That's good, right? Further, as far as bookkeeping is concerned, remember that first time that I evaluated the slow version of the Fibonacci function on the page and it blew up and it was awful? And then, you know, we wrote that human version of the Fibonacci function, and it was, you know, just a few steps, and it was very compact. Okay, by just making a minor change in the definition of the Fibonacci function. So we're going to do that for the multiplication function. So in particular, concerning the Fibonacci function, on the one hand, we had f from naturals to naturals, and we had defined it by f of n is 0 when n is 0, 1 when n is 1, and the sum of the previous two otherwise. So this is the slow one. This is the terrible, awful one. If you want to evaluate like the 100th Fibonacci number by hand, I mean, it's just not going to happen. Not if you use this one. The human one, in fact, to get the job done, we defined two functions, right? Two of them, in fact. We said, okay, you know, G just because that's the next letter in the alphabet, so it needs to have the same signature. Okay, but this G doesn't end up actually doing any work. The function where the actual computation occurs, we named G tilde, or G party hat, or what have you. And what was its signature? Well, yes, but I mean, you know, this function's signature is naturals to naturals. So my question is that concerning G party hat, what is its signature? Right, naturals, cross naturals, cross naturals to naturals. Okay, so what I'm saying is that F and G have the same signature, and they mean the same thing. So like G of 100, F of 100 means the 100th Fibonacci number. G of 100 means the 100th Fibonacci number. So what is the purpose of these two new arguments, right? Because we're saying that this G has just like one input, but this G tilde has two. What is their purpose? Yeah, they represent the lesser of the pair that you remember and the greater one. So that's where you can remember something. So now if you look back at that computation where I evaluated F at 7, you know, I ended up evaluating F of 1 13 times. And I evaluated f of 0 8 times. Or maybe it was 21, I can't remember. But it was a lot of times. And I evaluated f of 2 several times, and I evaluated f of 3 several times. Okay, so then the problem with this definition is, in a sense, that this function can't remember anything, right? It can't remember anything because, you know, functions don't remember anything in the first place. But this function only has one input, so that's all it can keep track of. Whereas this function has 3 inputs. So, in a sense, what I'm saying is that the purpose of these 2 extra arguments is where we can keep track of stuff. Okay? So to remind you, the definition goes like this, is that g evaluated at n will be g party hat evaluated at n, and then what are the next 2 arguments? And why? 0 and 1. So these are going to be 0 and 1. Why 0 and 1? Yeah, those are the first 2 Fibonacci numbers. I can remember those. That's where I start. I can remember those. Okay. Now, if we were to stop writing here, this wouldn't tell you at all how to calculate, right? Because we don't know what g tilde is yet. So g tilde evaluated at n, and a is the lesser of the pair that you remember, and b is the greater one. So this will have a definition like this. So again, we'll say what the answer is when n is the least natural. So that is to say, when this first argument is 0, what's the answer? It's A. We know a pair, and when n has reached 0, the answer is the smaller one. It's A. So if n isn't 0, that means that we have more work to do, essentially. So we'll evaluate g tilde again. And the question is what goes in the arguments? So what about this one? This will be n minus 1. Now, conceptually, the reason why is because, well, you could think of it like this. I'm about to write it. I'm going to calculate with it in a moment. And what you'll observe is that we'll repeatedly evaluate g tilde, and this first argument will be counting down. Like 5, 4, 3, 2, 1, 0. It'll be counting down. Okay? So that's its purpose. So when you say n minus 1, more or less what that means is that we've made one step of progress. Okay, what goes right here? And why? B goes right here. Now, why does B go here? Very good. So this is the pair that we currently know. So the question is, what's the next pair that we know? So currently, the big one, the big value, is B. But when you move one position down the line, that means that the little value is now B, because you're shifting. Okay, and what's the new big value? B plus A. Okay, so this is otherwise. Okay, and you know, for example, I could say, you know, if I wanted to evaluate g of 7, which was that terrible mess. Okay, if I was doing f of 7, it was a terrible mess. And then according to this, it'll be g tilde at 7 and then 0, 1, right? Why 0, 1? Because it's always 0, 1 to begin with. And why is it always 0, 1 to begin with? Well, because those are the first 2 numbers in the Fibonacci sequence. That's why. Okay, so then this will be g tilde evaluated at 6, 1, 1, G tilde evaluated at 5, 1, 2, G tilde evaluated at 4, 2, 3, G tilde evaluated at 3, 3, 5. So observing, notice that the first argument is counting down. It's counting down, and it's going to get to 0, which means we're going to stop soon. Furthermore, look at the second and third arguments. What they are is they're like a little window into the Fibonacci sequence. If you were to write it all out, first you see those, and then those, and then those, and then those, all the way down. So 2, 5, 8, 1, 8, 13, 0, 13, 21. Now that we reach 0, the answer is the lesser of the pair that I currently know. Okay. So, imagine that enormous computation that we wrote several lectures ago, and now compare it to this one. Which one's preferable? This one, by a lot. In the end, the reason why this works is because these extra arguments gave us room to remember something. So what I'm saying is that all of these parentheses here in the in our function, more or less, they constitute the same kind of problem as this slow Fibonacci function. The same kind of problem, but to a lesser degree. And we're gonna fix this one. We're gonna get rid of this problem using the same technique. We're going to have another variable, so it can be somewhere for us to remember. For us to remember something, so we don't have to have all these parentheses. Well, in the end, the way to think about it is, again, how would a human do this? So if a human was doing this, in the first place, if they were writing this all out, they probably wouldn't write all those parentheses, right? Probably not. Further, since they're not writing the parentheses, here I suspect a human would probably just write 20 instead of 10 plus 10, and then 30, and then 40, right? That's how a human would kind of go about it. So what I want you to see is that that kind of represents like a running total of the computation. Okay, so to define the multiplication function to where it has a place to remember the running total is like this. So I'll just write M for multiply. It'll have the same signature as mult in R. So it'll be this. And we want to calculate, we want it to be, n times x. And that's what we want the output to be. But like the Fibonacci function that has the auxiliary g tilde, so g and g tilde, we want an m tilde. Now what's going to be the signature of m tilde? So, this right here is going to be, n. This one is going to be x. And when all is said and done, this is going to be n multiplied by x. That's what they are conceptually. Okay, what about these? What's going to be the signature? Okay, good. We'll have n cross r. So it definitely has to be n cross r because it's got to have at least that much, right? So this will be n and this will be x. And then I heard you say cross r like that. Okay, then so what's that one going to be? Okay, this will be the running total. And then to r. All right, so let's see if we can figure this out. So just like for the Fibonacci function where we had g and g tilde, now we're going to do it with m and m tilde. Okay, so we'll define. So m evaluated at n and x. Well, that's got to be m tilde evaluated somewhere. It's got to be the same n and x. And then this position on the Fibonacci thing is where we were putting the first two Fibonacci numbers, right? My question is, what do we put here? 0? Why 0? Why 0? Right. So remember that is what we're doing is we're conceiving multiplication by a natural to be repeated addition. So you're adding over and over again. So if you're making such a sum, well, what is the value of the empty sum? 0, because that's the additive identity. 0 is the thing that's neutral with respect to sum. So this is 0. It's always 0, because that's the additive identity. Okay, so if we stopped writing there, then that wouldn't be enough to calculate yet. Okay, so we have to define what m tilde is. Okay, now we need to give a name to whatever you want to call the running total. So what do you want to call it? T? Sounds good. Doesn't matter as long as you don't call it, you know, m, m tilde n or x, right? Okay, call it T. Okay, so then this one is going to be piecewise defined with clauses. All right. So this one, again, this n is, when we're calculating, what you'll witness is that it's counting down. It's essentially what n represents is how many more steps do we have to go. So suppose that n is 0. We've made it to the least natural, which means that we need proceed no further. Then what's the answer? It's got to be t, whatever the running total was, right? So you're asking, you know, what is the answer when you've reached the end? It's t. Okay, supposing we haven't reached the end, then we need to call m tilde again, and it needs 3 arguments. Okay, it needs 3 arguments. What are those 3 arguments going to be? Okay, why n minus 1? Yeah, because we're counting down. That sort of basically signifies, you know, we've done, we're doing 1 step of work here. All right, what goes here? X, okay. Why x? Yeah, because that's what we're adding, right? So if I said, you know, calculate 10 pi, then you'd have to make, well, 10 copies of pi, right? You wouldn't make like 6 copies of pi and then 4 more copies of like 8, right? They all have to be the same. So this is just x. And then what goes here? T plus x. Or x plus t, doesn't matter. Addition commutes. Which is to say that, you know, we're making a running total, and to take 1 away from that is to add 1 to the running total. So that's just another way to say that, yes, it is the case that 5x is in fact a single x plus 4 more of them. All right, so let's evaluate and make sure that this makes sense. So how about m of 4 and 10? Okay, so what is this? How do we do that? Right. So the definition of m of two arguments like that is, well, you immediately evaluate m tilde. The first two arguments are the same, so 4 and 10. And then the last argument is 0, which is to say that, all right, we're starting our running total at 0. Fine. So now, concerning this, notice that n is 4. Okay, so we're going to repeatedly evaluate clause 2 as n counts down until we get to 0. All right. So this would be m tilde of 3, 10, and now we're going to calculate 0 plus 10, which is 10. Now, MATLAB is able to do that immediately. It doesn't have to wait. The reason why it has to wait right here, in this case, the reason why it can't do that, for example, drop the parentheses right now, is because you're still asking MATLAB to do that. So that's where its attention is. Its attention can only be in one place at a time. So in a sense, it's leaving, you might think, like these breadcrumbs behind. And then when it reaches the end of the rabbit hole, that's when it goes back and collects them all. But the way this is defined, it's able to perform this addition right now. Okay. Similarly, m tilde, 2, 10, 20. M tilde, 1, 10, 30. M tilde, 0, 10, 40. And now what? The answer is 40, right? Because our counter has counted down to the least natural, and so the answer is whatever the current running total is, 40. So, do we get the correct answer? Yeah? Is there less bookkeeping and breadcrumbs and things like that for MATLAB to remember? Yeah? And in fact, you can compare these, and generally speaking, MATLAB will execute this definition quicker than that one. It's quicker. It's not a lot quicker. It's a little bit quicker. Because, well, in the end, the reason is kind of a little bit technical. And I'll pass that on, pass up discussing that any further for the moment. But MATLAB can execute this one faster, but not like momentously faster, just a little bit. Other programming languages besides MATLAB would be able to execute this one extremely quick in comparison to the other one. Good. So that's the way that we can have less bookkeeping. So the way to have less bookkeeping, one of the ways to achieve it is to write an auxiliary function that has more arguments so it can remember more things. Okay. This technique, the technique of adding new arguments, for example, to the Fibonacci function or to the multiplication function, the name of that technique, it's not necessary for our class, but just for your interest, it's called memoization. And I didn't just mispronounce memorization. Rather, the word is memo, like writing something down. And so memoize means to write things down as they happen. So the technique is called memoization. Good. So now we want to address that we'd like to be able to perform the multiplication 100 times x, but not use 101 steps. We'd like to use less. Here's the main idea. This is kind of where we ended last time, is that if the request is multiply 100 and x, then you can do it in the following way. You can say, well, I'll say that x0 is 0 and x1 is x. And starting from that definition, now I'm going to start defining, well, x2, that's going to be x1 plus x1. Okay, so now I want to start keeping track. how much x do I have? So this x0, that's 0 x's. Right, this red is not computation. This is just me keeping track. You know, because strictly speaking, we can't write that red stuff. So this would be 1x. How much x is this? That'd be 2x, right? And then x3 is going to be x2 plus x2. x2 plus x2. And how much x is that? 4x, right? So specifically what I'm going to do is I'm going to repeatedly double the number of x's that I have by always adding the previous one to itself. So x4 would be x3 plus x3. That'd be 8x. x5 would be x4 plus x4, 16x. x6 would be x5 plus x5. So let me write this down so I don't lose track. 8x, 16x, 32x, and then x7 is x6 plus x6. So that'd be 64x. And that's neat, but I don't want to proceed any further because after all, we're supposed to go to 100. If I continue in this same fashion, the next one I'd get would be 128, so I would overshoot. So that's not right. So I can therefore say that the answer is that x8. The answer should be, well, we'll start with x7. That gets us most of the way there. Right, that's 64 x's. So that's not enough, but that gets us most of the way there. And then, well, to that, I suppose we could add x6, right? Because if we do that, how much x would that be? That'd be 96, right? So we're not quite there yet, right? Should I add x5? No, that'd be too much. Should I add x4? Nah. How about x3? Oh, this one is just right? x3. All right. So what I'm saying is that you know, the mult in R function and the m and m tilde pair function, for that matter, the way that they achieve 100 multiply x is they do 101 steps. Okay, they do 100 additions. Now, how many additions do we do right here? Well, we can just count them, right? 1, 2, 3, 4, 5, 6, 7, 8. And that's, you know, less than 100, which is the point. And further, you know, if it says 100, but if I was to change it to a million, then mult in R would want to do basically a million adds. But if you were to do it like this, it'd be only like, you know, like 20 or so. It'd be around 20, and 20 is a lot less than a million. Okay, so there's an idea. A second idea that I want to bring up is suppose I give you this number. I say 2370.2018, and suppose I say, well, I want you to divide this by say like 64, maybe, and here's another one, 2370.2018, and I'll give you a much bigger number to divide by, like 1,000. So suppose that concerning these two, you know, you learned how to do this in grade school, you know, with the division algorithm, you know what I'm talking about, in the house and then all that stuff. You know, the thing that looks like this. You got stuff outside and inside, whatever. So if you wanted to do this, suppose I said that you can do either one of these. I need you to do one of them. Which one would you choose to do? The second one? Yeah, but why though? I mean, look, this number is so small compared to 1,000. Surely this one would be much easier. Ah, right. So division by 1,000, okay, you know, that means shifting the point 3 positions to the left, right? So divide by 10, another 10, another 10. So dividing by 1,000 is like the easiest, you know, it's extremely easy. You just take that point and move it 3 positions to the left. Similarly, if it wasn't divide, if it was multiply, that would mean moving the point 3 positions to the right. And even if this was a million, it doesn't matter that a million is much bigger than 64, because a million is still going to be particularly easy, because that corresponds to a shift of the point, 7 positions. That's it. And then you just have to remember to fill in zeros, you know. You remember the rules. So so the way that we count, because we count in base 10, this is actually quite easy to do compared to that. Now, by the way, why do we count in base 10? 10 fingers. That's the only reason. Okay, and you know, essentially every existing culture in the world counts in base 10, and of those that don't count in base 10, essentially all of those count in base 20. Why 20? Fingers and toes, probably. I mean, it's just that simple. And if we found 8-fingered aliens, I guarantee they'd count in base 8. Okay, I guarantee it. So here's the deal: is that whatever base you count in, multiplying or dividing by the base is what's easy. So because we count in base 10, multiplying or dividing by 10 is easy because that amounts to a shift of the point. Okay, a left shift or a right shift. Left shift for a division, right shift for a multiplication. If our 8-fingered alien friends, you know, if they came to visit us and wrote down their stuff, multiplying or dividing by 8, powers of 8 would be easy, so that this one would in fact be much easier for them. Okay, this being 8 squared. Okay, which raises the question, I hope, that you know, we're asking in the end, we're asking a machine to perform arithmetic. What base does the machine count in? Base 2. It counts in base 2. So we count in base 10, and that makes it easy to multiply and divide by 10. The machine counts in base 2, which means it's easy to multiply and divide in base 2. Okay, now it's not too necessary to know this part, but I'll explain it. In the machine, there are billions of little devices where a voltage goes in and another voltage comes out, and the name of these the devices I'm speaking of, they're called transistors. Transistor, like that. And what happens is that plotting as a graph, if this is the input voltage to the transistor voltage, and this the output voltage, then as you increase the voltage on the input wire, what ends up, basically what happens is it stays very flat. So the output voltage is essentially constant as you're increasing the input voltage until you reach a certain critical voltage, and then the output voltage spikes rapidly and plateaus to a higher voltage. So what I'm saying is that concerning the input voltages on the transistor, if the voltage is low, if the input voltage is low, then the output voltage is low. And it can be anywhere in here, it's essentially constant. And then when you pass this certain critical voltage, then the output voltage is high. So what a transistor is, it's a little machine that you can mess with the voltages on it, and then suddenly when you turn the knob just past the critical place, then suddenly its output goes bloop. It turns on like a light bulb. The name transistor is, you know, sort of a mashing, a portmanteau of resistor, which is a different electrical device, and transition. So this is a resistor that goes through a transition. So what's happening in the machine is that when you're considering bits of data, if the voltage on that particular component is low, that's interpreted as a 0. And if the voltage is high, it's interpreted as a 1. That's why machines count in base 2, because they're constructed of transistors, and transistors either maintain a high or a low voltage. 0 and 1. And as a result, multiplying and dividing by 2 for a machine that counts in base 2 is cheap, in the same kind of way that we can multiply and divide by 10 on the cheap. All right. So what I'm saying is that what we're going to do now is we're going to take this function, and what we permitted ourselves to do, wait a minute, yeah, what we permitted ourselves to do was to add. That was the only thing we permitted. Okay, because we were saying that's the only thing we know. And now I'm going to say that we're going to make a similar function, but besides being able to add, we're also going to be able to multiply and divide by 2. Now that's permitted. That's going to be permitted because for the machine, that just means a shift of the point to left or right. Okay? Also, in this same idea about bases, besides multiplying or dividing by the base being easy because it's a shift, another thing that's easy to do is to detect whether or not the number in question is a multiple of the base. So, well, looking at a number that's represented in base 10, to like all the numbers you've ever written, that's an integer. Forget the decimals. How do you tell if it's divisible by 10? Yeah, the least significant digit has to be 0, right? So like 0 is divisible by 10. And so is 120. 120 is divisible by 10. But 123 is not, because the least significant digit is 3. And divisible by 10 means that the least significant digit must be 0. Similarly, if you were to write a number in base 8, in octal instead of decimal, then it would be divisible by 8 if its least significant digit is 0. Similarly, in binary, which is to say base 2, it's the exact same story. If the least significant digit is 0, then it's divisible by 2. If it's not 0, then it's not divisible by 2. Okay, so for that reason, it's very easy for machines to check whether or not something is even or odd. It's literally just like us looking at the page and asking, is that number divisible by 10? Yes, because the least significant digit is 0. Finally, I do want to mention that, well, the number 25. So when you're talking about bases in a math class, and well, when you're not talking about bases, you just write 25, and it's understood that that means in base 10. Okay, but when you're talking about bases in math classes, you usually you write a subscript to say that this is 25, and that's understood to mean in base 10. So as it happens, in base 10, 25 is 8 plus 8 plus 8. That'd be 24, and then plus 1 more, right? So what, and another way to write 25 is 10 plus 10 plus 5. So as a result, what this means is that concerning 25, how many 10s does it have? It has 2 of them. And then there's 5 more. That's what 25 means. But if you wanted to write 25 in base 8, well, how many 8s go in there? 3 of them go in there, and then you'd have 1 more. And so sometimes when you write 25 like this with a subscript 10, that's one style, but another way you can write it is like this, so dec 25, which means decimal 25. And so notice that because there's 3/8, in octal you'd say that this is 31, because it's 3/8 and then 1 more. So what I'm telling you is that this is the reason why mathematicians have a difficulty time telling the difference between Christmas and Halloween. Because dec 25 is oct 31. Good. Now that we're past that, now we can get to business. All right. So then we're going to define mult in R2. So, okay, you have to be dedicated to tell a joke like that. Okay, it takes a lot. It takes a lot of dedication to deadpan it, and to be ready to say it. Okay, so mult in R, and we're going to call it 2. In the end, the reason why is that this is going to use the binary trick. Division and multiplication by 2 are going to be permitted. So we'll have in cross R to R. And we'll define it like this. So mult in R2, evaluated at n and x. So now, this one is not going to be the memoizing version of mult in R. It's not going to have its auxiliary pair. It's not going to have one of those. At least not on this page. We might have an exercise where you have to do it. All right. So, fine. When n is 0, that means that we're talking about 0 multiplied by x. So the answer is 0. Okay. Now, if this was exactly mult in R, we would just say otherwise. But we're not going to do that. Instead, we're going to use this arithmetic involving 2 trick. So in particular, the next clause, I'm going to say if n is even. And that's extremely easy to check, because that's literally where the machine is concerned, just asking, is the least significant bit meaning binary digit, is the least significant bit 0? So if it's 0, then we're going to do this. So specifically, n multiplied by x, that's what we're doing. So we're saying that division by 2 and multiplication by 2 are cheap and permitted. So isn't it the case that n multiplied by x, when n is even, is the same as n divided by 2 multiplied by what? What do I need to put in here for this to be right? 2 multiplied by x, right? So when n is even, this division is cheap. That's shifting the point, one position. And x is just a real, that's shifting the point in the other direction. So this is a left shift and a right shift. Okay, so that's true, and that's what I want to write in this clause. So what do I have to write right there to make it work? So I'm going to call this function, same function, mult in R2, and what are going to be the arguments? Well, n over 2, right? And what? 2x. When n is even. Okay, and then otherwise, of course that means n is odd, but I'm just saying otherwise. Otherwise, we're going to do the exact same thing as mult in R. we're going to do the same thing where we just take out an x. And say, okay, this will be x, and then plus mult in R2. And then what are the arguments? N minus 1 and x. So to a large extent, this is exactly the same as the previous mult in R, except we're including this clause in the middle. When n happens to be even, we do this switcheroo, and we say, well, we'll divide the n by 2 and multiply the x by 2. All right. So let's see how it works. So for example, I'll evaluate mult in R2 of 100, and I'll just write x to keep it abstract. Okay, so oh yeah, and I want to mention that notice these clauses here. Clause 1, clause 2, and clause 3. Remember that the rule is that clauses match top to bottom with first match. The reason why I want to say that is because here we have a clause that's asking about if n is even. Okay, but how about 0? Is 0 even or odd or what? 0 is even. It's even. With the representation idea and base, when you write 0, is the least significant digit 0? Yes. So it's divisible by 2. And 3 and 10 and everything else. Alternatively, if I have put a pile of 0 M&Ms in front of you. Please break that pile into groups of size 2. Okay, now that you've done that, how many are left over? 0? Ah, that means that 0 is divisible by 2 because you didn't have any left over when you were finished. So 0 is even. Understand, however, that when the first argument is 0, you'll hit the first clause because the first guard is true. The second guard is also true, but you go to whichever clause's guard is true first. Okay. So to that end, 100 is even, so I'll use the even clause. So this is mult in R2, and then what are the arguments? 50 and 2x. And remember, you're to understand that 2x means that the machine takes that x and then shifts the point 1 position to the right. That's what that means. Okay, then 50, I'll use the even clause again. Mult in R2, and then what are the new arguments? 25 and 4x. And remember, you're to understand that that means that the machine took the x and shifted the point right twice. So that's a cheap thing to do. So that's 25. Ah, now we have 25 is odd. So now which clause? The otherwise clause, right? Clause 3. So this would be, we take out the 4x and write 4x and then plus mult in R. And then what are the, in R2. And then what are the new arguments? They are 24 and what? 4x. So observe, we were like on a roll, We used the even clause twice, then we kind of got like clogged up, and used the odd clause. But do you observe that the effect of having used the odd clause once is now we're going to use the even clause again, right? Because you take any odd number that's positive and subtract 1, then you have an even number. All right. So then this will be 4x plus mult in R2, 12, and 8x. And remember that this means 8x. Understand that that means shifting the point 3 positions to the right. That's what that means in a binary number, right? Shift, shift, shift. So 4x plus mult in R2, again the even clause, so this would be 6 and 16x. 4x mult in R2, 3 and 32x. All right. So do you observe that? Well, 4x came out, a little bit ago, and do you observe that now 32x is going to come out? What do you think is also going to come out? 64x, probably, right? And I claim that that should be no surprise whatsoever. Why should that be no surprise whatsoever? Well, yes, but I mean, isn't that what we just showed 2 pages ago? Yeah. So this will be 4x plus 32x plus molten R2. So we take 1 away, so 2 and 32x. So we took out a 32x. Now we have even case again. Oh, we're back to the odd case now. So can you see that 64 will come out now? So 4x plus 32 x plus 64 x plus mult in R2 of oops, yeah, oh no, I did it, 0 and 64x. And now finally the first argument is 0, which means that this function evaluates to 0, and we get this. Okay, and I didn't write all the parentheses, okay, but the machine, in a sense, hasn't done any of this, and now it starts going backwards. It sort of goes backwards and works it all up and then makes 100x. What I want to say is, what I want to point out is that this one did not do this with the running total. Rather, it's kind of leaving these breadcrumbs behind. So, you can imagine writing one of these, a function like this, but giving it an auxiliary argument to where it keeps track of a running total. Any question about this? So we wanted to multiply by 100. Now this is a little bit of work, no dispute, but mainly it's just because I'm writing it with a pencil. Okay, the machine can do this quite quickly, and by the way, how many clauses did we evaluate? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Whereas if we were to use molten R, the original one, with 100, we would have had to evaluate 101 clauses. But here we just did it in less than 10. Interesting. Any question about this? So it may be interesting for you to know that when you type something at the machine, when you type it and then press enter, say like multiply these two numbers together, the actual hardware is doing something very similar to this. In fact, something just like this. In fact, it's doing it. The most similar thing would be with an auxiliary function, because it is actually keeping track. It does have a running total where it's doing this. Interesting. Any questions before we move to the next thing? Yes?
What is so can the machine, does the machine know how to multiply?
Yes. What I mean is that you could get at, what I mean to say is that this even odd idea that we're doing right here, we could literally go over to the lab, okay, and dissect it and take out the processor and get out a microscope, and we could look at it real close, and you'd see all manner of wires and circuitry all over the place. And if you knew what you were looking for, you would see something that's doing exactly this. Well, exactly this if we were to modify it to have an accumulator. an extra argument, an auxiliary function, is doing exactly this. So the machine knows how to do it, just like you know how to do it. But the point here is not for you to show me that you know how to multiply, but rather that you can write a function. Other questions? All right, good. So another idea that's in the same same kind of vein of ideas. This even-odd business. So what we were just looking at is sort of how to break the problem into two different kinds of parts: a part which can be reckoned as even, and a part which can be reckoned as odd. And a general technique in programming to make things go quick, or even at all, is to take one big problem that you have, and you want to break it into smaller problems, and solve the individual problems, and then combine them up to make the solution to the big problem. It could be something. This happens all the time. It could be as simple as you and your buddies run a cleaning service, and you say, okay, I'll clean the south half of the building and you the north, and then all together, that's the whole building. Okay, to that end, we're going to play a game called Guess the Natural. And the way this works is that there's two players. Well, I guess you can call them players, but there's the person who knows the answer, and then there's the person who's trying to guess. So we're going to refer to those as the oracle and the player. So the oracle knows. The oracle knows the truth, and the player has to have 20 questions. More than 20 sometimes. Okay, so the oracle. What they do is that they select a natural, but they keep this to themselves. So only the oracle knows that, and also select A and B in the naturals, such that A less or equal N less or equal B. Okay, so that's kind of like a overly precise way to say, I'm thinking of a natural between 1,000 and 5,000, something like that. So I told you A and B, but I'm not telling you the one I'm thinking of. Okay, and then you tell the player the values A and B, and I'm writing that as a closed interval. But don't misunderstand. I'm not talking about I'm talking about only the naturals that are in there, not all the reals. So you tell the player that, and the player, comes up with a guess. Guess is M in the naturals. Of course, it is an error if the at any rate, it will be construed as an error if the player guesses a natural which is not in there. So if I say something like, I'm thinking of a natural between 1,000 and 5,000, and you say, is it 3? No, it's not 3, right? It's between 1,000 and 5,000, right? So it's got to be in there. The player guesses that, and the oracle responds. Oracle responds with one of. So the oracle will respond with -1 if M is too low. Zero if M is correct, and 1 if M is too high. All right. So yes?
Wait, so the oracle selected n, which represents the correct word.
The correct answer.
So how could n be correct?
M?
Yeah.
Well, I mean, you know, if I say I'm thinking of a number between 1,000 and 5,000, you could just make a guess. You could say, is it 1,000? And I'll say, no, that's too small. Or you could guess and say, is it 2370? And then I'll say, you got it. Right? That's what I mean, is you make a guess somehow. So, you know, one way to go about this is you could, you know, sticking with what I said, I'm thinking of a natural between 1,000 and 5,000. You could just like make a list of all those naturals, 1,000 to 5,000, and then you could just start guessing at 1,000. You say, is it 1,000? And I say, no, that's too small. So you cross 1,000 off the list. Is it 1,001? And then, no, that's too small, and you cross it off the list. Okay, so you can imagine this process is going to end, right? It's going to end because, after all, there's only 4,001 choices. So it's going to take at most 4,001 guesses. Now, if I've chosen randomly in there, then on average, it's going to take you half of that. So if there's 4,001 choices, it's going to take you about 2,000 guesses, right, to guess the correct one. So you could just start crossing them off the list from small to big. Or you could cross them off the list from big to small. Or you could just always select a random one and cross it off the list. Or say, I found it, if you happen to find it. But there's a much better way to go about doing this. There's a much better way to go about doing this because, you know, if we're playing the game and I'm the oracle and you're the player, I'm not saying just yes or no. I'm not just saying you got it or you didn't. I'm saying that your guess was too low, your guess is correct, or your guess is too high. I'm giving you much more information. So besides just randomly guessing, what's a better guess? Yeah, how about you guess the middle? Right, because let's consider. If I say I'm thinking of a number between 1,000 and 5,000, then what number's in the middle? 3,000, right? You average them, right? 5,000 plus 1,000 is 6,000, over 2 is 3,000. So you guess the one in the middle. Now, there's only 3 possibilities. If I say you got it, then you're done, right? Way to go. If I say that it's too small, that you've guessed too small, then you can cross 3,000 off the list, because 3,000 is too small. But what else can you cross off the list? You can also cross off 2,999 and 2,998, and in fact, everything that is to the left of 3,000, right? So if you guess the midpoint, then that means that if these are all the choices, and you guess right there, okay, and the response is that that's too low, then do you observe that that means that you have cut the problem in half? Okay, so then you would guess, then you have a new interval. You guess the midpoint again. And you either get it right, you either got lucky and got it right, or you have decreased the problem size by half. So the last thing, and the thing I want to leave us with, is something like this. Suppose that I say I'm thinking of a number. I'm thinking of a number between 0 and 1,000,000. I'm thinking of a number between 0 and 1,000,000. That's a lot of choices, right? That's 1,000,001 choices. So if you did it sort of naively, it's going to take you 500,000 guesses on average if you're doing it naively. But if you're doing it like this, where at all times you either find the answer or you cut the problem size in half, the question becomes, how many times can you cut the problem in half before there's only one choice left? How many? So it's going to be about 20 times. So let's check that and then we can leave. So that number on the calculator is 1,000,000. So if I say ANS for answer, like on MATLAB, it's 1,000,000. So if I type ANS over 2, that's 500,000. And now A and S is now 500,000. So that's 1, 2, 3, 4, 5, 6. And now it's going to start having a decimal point, but in reality, you'd have to, you wouldn't say, Oracle, what do you think about 3.5? You don't ask the Oracle about 3.5 because 3.5 is not a natural number, right? So you'd round it. 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. And I heard someone say it. I had to press the button. I might have been off by 1. It might have been 20, it might have been 19. Doesn't really matter. What is the name for the number of times I need to press enter to get down to 1? Logarithm base 2. Right? And that's what's making all of this work. Good. So I hope you have a wonderful Thursday.